Hi, my name is Ayush, and in this video, I'll be building a logistic regression algorithm from scratch using only numpy to identify if an image is a cat or not a cat. So the main task in logistic regression is generally classification for 1 for yes and 0 for no. And for example, in our task of identifying a cat, these images that are a cat would output 1, and the images that are not a cat would output 0. So trying to show internally how it works, you've probably seen an image like this, which is an image of a neural network, where we have some inputs and we do some calculations and we eventually get an output. So what logistic regression is it's a neural network with no hidden layers. So we don't have any of this in between. We just have the input and the output, as you can see over here. So we might have some input numbers like 5, 3, 6, and we'll do some calculations with these numbers, and we'll eventually output either a 1 for yes, the image is a cat, or a 0 for no, the image is not a cat. Before we actually begin building the neural network, we first need to process the dataset. So the dataset has two components, test data and train data. So we'll use the train data to train the model, and test data to test the model on different inputs. And as you can see, these are the file names of the dataset, and we only want to be able to read. So now let's see the components of the dataset so we can actually store it as different variables. So let's print out the keys of any one of them. Keys. And let's see. So each dataset contains train set X and train set Y. So let's try and store these as arrays in our database, in our file. Okay, so now we have all the different datasets stored in our variables. So now let's see the shape of the X and Y train data, so we can see like how we need to process it. So we can see it's 209, the shape of X is 209, 64, 64, 3. So essentially what this means is that 64 by 3 represents one image, and in our train data we have 209 images. And the 209 comma this means that we have like an image representing, how do I say it, like 1 0 1 0. This means yes, it is a cat, 0 not a cat, 1 yes a cat, 0 cat. So we have 209 rows to represent each image in the train data. But to actually process it, we need to transform the shape of it. So let's quickly transform the shape. Train set X equal to train set X dot reshape. And the shape is going to be, so what we want is we want each feature to be in one column. So we'll transform the matrix in such a way that this is now going to be our new matrix. There's some overlap here, that's fine. And each column will represent one image. So we'll have 64 into 64, 64 into 3, which is 12,288. And we'll have 12,288 inputs in each column. So, and I'll represent one image. So one column input here, one here, one here, and one here. And one way we can do that is just by doing set X shape 0 minus 1, and then we can transpose that. And let's do the same for the test set X. And minus 1. And transpose essentially means we convert all the rows to columns and all the columns to rows. .d. And now for the Y shape. So originally Y is something like this, but we want it like this, so we can actually process it. So we'll have 1 0 1 0, and we can do this by simply doing train set Y shape minus 1. And let's do the same thing for X very quickly. So now if we print out the new shapes, let's print out the shapes again, and we'll be able to see once. We'll see we now have it in the correct way we want it. So we have this shape for the inputs x, and we have this shape for the input y. And one more thing that we normally do is mainly as like a regularization thing, is we should divide it by 256 to make sure it doesn't explode. Let's do a train set x divided by 255 is better. X put test set x divided by 255, and that's how we process the dataset. Okay, in terms of the architecture of the model, there's two main things that comes to building a logistic regression algorithm. The first one is the forward path, which is called forward propagation, and the second one is backward propagation. So we use forward propagation to actually calculate our output, and we use backward propagation to optimize our output and make sure the model is actually good at predicting it. So quickly, how forward propagation works is we'll have multiple different weights and inputs. For example, let me label these quickly: x1, x2, x3, x4, and x5. So essentially what we'll do is we'll do x1 into w1 plus x2 into w2 plus x3 into w3, and so on until we reach xnwn plus xnwn, and that will be the value of this. And we then add it by a bias, which is a fixed term generally, which is changed during backward propagation, and then we add a bias, and then we apply an activation function. So an activation function is to make it non-linear. So right now this is a linear function, so it can't really capture like more finer details or non-linear details. So that's why we use the activation function. And in logistic regression we use sigmoid. The sigmoid function is over here. And one really good thing about this function is that it squashes any input between 0 and 1. For example, if we have input minus 100, it will become very close to 0. And if we have input 100, it will become very close to 1. And this gives us a probability which we can use later on to determine if the image is a cat or not a cat. So basically, if the probability is higher than 0.5, it is a cat, otherwise it's not a cat. Okay, now let's work on actually implementing the forward propagation. So first we'll need a sigmoid function. It's not necessary, but it makes it much cleaner. So return 1 plus p.x minus e, and this is essentially this function exactly written in numpy and written in Python. And then before we can actually implement the forward propagation, we need something to work with. So we need to initialize these weights and this bias over here. Initialize. And we'll need the input of x so we can figure out the shape of the weights and the weights matrix. So w is equal to x dot shape 0 and 1. And then I forgot the main thing. Okay. So essentially this np.random.random is a function to give it random values, and these random values will then be changed later on with backward propagation. And we can make bias a random value, but it's just much easier to make it 0.0, which is a float value. And then we have to return w and b. And then let's actually implement the forward propagation. And for this, the inputs we'll need will be our inputs x, w, the weights, and the biases. So our step 1 will be to calculate like this thing over here, and we can simply do this by doing like a vectorized form of this, which is w dot t in and then matrix multiplication by matrix x, and dot t is transpose to preserve matrix dimensions and allow matrix multiplication. So we can do z is equal to w dot t x plus b, and then we can compute the sigmoid function just by doing a is equal to sigmoid of z, and there we have our forward propagation. So we can then return a. So now that we have done forward propagation, let's work on calculating the cost. So the cost is essentially how far is our output from the expected output. And for this, we have a formula over here, which is called binary cross entropy loss. This is a formula where n is the number of training examples, and we want to iterate all the way from the first training example to the last training example, and then take the average of all of that, and that's the average cost. And the loss would be just this part, like just one example, and the cost is all examples put together. So let's write this function once in Python. So we can write def cost. So, and we need a number of training examples, which can be x.shape 0. We also need the input x over here. Oh no, it's x. And then the cost will be, let's just copy from here. So we have -1 divided by m, which is the number to average over all the training examples, and then np.sum is a function we can use to calculate the sum over all the examples. So we have, we also need y over here, I believe. Y, and we also need a from the other function, x, a, and y. So we have y into np.log a, and then it's plus 1 minus y again into log np.log 1 minus a again. So this will be our cost, and then we can simply return this cost. And now let's get into the actual backward propagation, which is probably the hardest part of logistic regression. So in backward propagation, our task is to find the partial derivative of each weight with respect to the cost function. So what we want is the derivative of the cost with respect to W1, cost with respect to W2, and then so on until we reach the cost with respect to Wn. And then we also want the partial derivative of the cost with respect to the bias. So essentially, these are all the formulas that are involved in calculating the cost from the weight or the bias. So one thing we can use is a chain rule to figure out the exact partial derivative of the cost with respect to any weight. So one thing we can do over here is that this over here is z. So we can say the derivative of z with respect to w, and then we can call this over here a. So we have the derivative of a with respect to z, and over here we can say the cost c. So derivative of cost with respect to a. So then something happens that we can cancel out all of these, and we end up with the partial derivative of cost with respect to weight. So once we calculate all three of these derivatives over here, we'll land on three pretty cool formulas. So we'll get dw to be equal to dw is equal to 1m into x, and then the matrix multiplication of the activation minus y, and then we take the transpose of this. We'll find that db is equal to 1 over m into np dot sum into a minus y. And you can actually derive this by doing the calculations if you know calculus. But one interesting thing over here is that even in most cost functions, like all of the popular cost functions like mean squared error or this binary cross entropy loss, or the value, if you take it with respect to value, the derivative of the weight often comes out to be the error. So the error over here is a minus w into the input x, and the derivative with respect to bias will come out to be just a minus y. It'll be just the error. So now let's actually write those formulas in the Python script. So let's do it backward propagation. I spelled backward wrong. And our inputs will be x, and then we'll need a and y. So we can find the number of examples from x.shape 0. And dw would be equal to the formula we derived previously, which was 1 over m into into x, and then matrix multiplication of a minus y, and then the transpose of that, a. And then db, the derivative with respect to biases, would be same thing but just the error. So the np.sum over all the errors, a minus y. There we go. Oh. And then this function will return dw and db. So now that we have the backward propagation done, so actually optimizing the model is actually very easy. So it's a simple formula: w is equal to w minus the learning rate into dw. So the learning rate over here is a hyperparameter. That means it's something that we set. The model does not decide. So for example, if we have a graph like this and we're trying to reach the minimum of the cost function over here, if our learning rate is too big, then the w might end up going over here, then here, and we'll never actually reach the w. And if our learning rate is too small, we might go here, and we'll never actually reach the cost function. Like you have very small jumps. So finding exactly the right learning rate is a very important topic in machine learning, and there's lots of algorithms to figure it out and intuition. But like having a set learning rate for now is fine. So let's actually implement the model now. Yeah, to optimize, we'll need w. We won't need w. We'll need x. We'll need y. Okay. So we'll need a function cost, so we can like keep track of the cost in every 20 iterations. We'll need inputs of learning rate and iterations. So we have to loop like for the number of iterations. So for I in range iterations, first obviously we need to initialize the parameters first. So let's just copy. That'll be wb is equal to initialize x. So now we have w and b, and let's actually optimize it now. So we'll do a forward propagation pass. Forward propagation, and for that we need the inputs x, w, and b, and that will output, what is that output? A. And then we'll do a backward propagation pass. So we'll just copy this. So we have dw and db is equal to that. Then we'll actually optimize it. So we have w, and then we can do minus equal, which is a faster way to do it in Python, and that'll be the learning rate into dw, and then the same for the bias is equal to learning rate into db. And just so we can like keep track of what the model is doing, one thing we can do is like every 20 iterations it should print the cost. So if I20 is equal to 0, then cost is equal to compute. What's it? Cost x, a, and y. Is it that? Yes, that. And we can add that to the cost. Append cost. And let's also print that out once using the s string. So the cost is, let's print out cost at iteration, and let's also print out the iteration so we can keep track of it. There we go. And that is our optimized function, and we'll want this to return wb and cost. So return wb and cost. Okay, now that we have the optimized weights and biases, one important thing is to to know what the output is for any given dataset. So we can make that a function called predict, and the inputs will be the same as the one for the forward propagation, x, w, and b. So then we can do a forward propagation pass on this. That'll be a forward propagation x, w, b. Is that the inputs? Yeah, that's the inputs. And a. Then we can make the y prediction be y prediction is equal to a greater than 0.5, and then this will output like true, false, true. But then to calculate the mean later on, it's good to make this an int. It's good to keep this as an as type int. And now let's actually make the model that combines all these parts to give us a fully operational logistic regression algorithm. So the inputs can be learning rate, iterations, and then we'll need a test set and a train set. So test set x, test set y, train set x and train set y. So let's actually combine everything we've done till yet. So mainly everything will be in optimize. So optimize, and this will output WB and cost. And cost is equal to optimize. And our xy we want to optimize off the training data. So that'll be train set x and train set y. We don't really need the input of y in this. So oh no, we don't need the input of y. Yeah. Train set y, and then we can predict it. We can predict based on the test data. So let's do we forgot to return y prediction over here. Y prediction, and we'll have y prediction is equal to predict of the test data. So test set x, w, and b, which we found from this over here. So now we need to calculate the accuracy. So one formula I have is just this formula over here, and it calculates the accuracy for the test data. Let's just confirm it's right. Yeah, there we go. Make sure everything's capitalized properly, and then we can print the test accuracy. And I think that is our model done. Yeah, that is our model now mostly done. So now if we run this model, and we can make a learning rate, let's make a model learning rate like 0.06, 1000 iterations, and then we can input all our datasets that we made, the datasets that we made over here, these datasets. Test set y, train set x, train set y. Okay, now I'm expecting some errors, so let's debug the model. Okay, did you mean A? So in backward propagation, I believe we put capital A by accident. Yeah, we did. So let's just fix that over there. Now that we fixed all the errors, let's try running the model once. And you'll see that as the iteration goes on, the cost goes down. So 0.7 to 0.4 to 0.2, and ends up being very low. And the accuracy ends up being 70. So you might think this accuracy low, and it is low because we haven't optimized any hyperparameters. So just for demonstration, if I made the learning rate very high, like 0.06 in this case, then the learning rate will bounce around from 0 to 11 to 2 and so on. So, and one more concept you should know about is overfitting. So let's also measure the train accuracy. That means like the accuracy of the training set. So I'll just copy this over here. And y prediction, train set y, and let's just also copy this. So one thing you'll notice is the train accuracy is much higher than the test accuracy, and this is not always a bad thing, but sometimes it might be the case that the model will learn too much about the input features, and it'll have a very good performance in the training set and a below average performance in the test set. So as you can see, the performance over here is 100% for train set and 70% for test set. So even that's an important concept to know. So thank you.